Hello, everyone. So we're going to get started. I want to thank everyone for joining us for the Last Mile Autonomous Delivery Systems panel discussion. My name is Tessa Green, and I'm the Program Director for the UT Grand Challenge Good Systems. I want to first, before we get started, acknowledge the significance of today, September 11th, a day that marks a moment in recent history that is still felt deeply by many across the country. The images of my experiences in New York City are as vivid now as they were on that day 19 years ago. While this year is also marked with immense loss and continued uncertainty, I'm really proud to be part of a program committed to making a difference for those around us. Good Systems brings together students and researchers from more than 24 schools and units on the UT campus to investigate how we can design AI technologies that benefit society. The team of researchers you will meet today has been working on just that, a robotics project to provide contactless deliveries that reduce person-to-person interactions. But I'll let them tell you more about that. Before we do, though, some housekeeping. All attendees will be muted and videos will be off. This panel is being recorded and will be shared with registrants following the event. During the panel, we invite you to put questions in the Q&A. You can do this through the Q&A tab on the Zoom menu. You are also encouraged to upvote questions so we get the most popular questions in front of our panelists. The chat is open, and we ask that you please be respectful in this space. We will not be monitoring the chat for questions, so remember, please use the Q&A function for that. And last, we will be sending out a survey following this event, and we would really appreciate your feedback. I want to thank the UT partners who have been working on this project with Good Systems. The Autonomous Mobile Robotics Laboratory, Human-Centered Robotics Lab, Learning Agents Research Group, Texas Robotics, and Urban Information Lab. Now, it's my pleasure to introduce the panel moderator and member of the Good Systems executive team, Peter Stone. Peter is the founder and director of the Learning Agents Research Group, part of the Artificial Intelligence Laboratory in UT Austin's Department of Computer Sciences, as well as Associate Department Chair and Chair of Texas Robotics. Peter was a co-founder of Kojitai Incorporated and is the Executive Director of Sony AI America. Given that resume, it's no surprise to hear that Peter has worked with each of our panelists at the University of Texas at Austin. Peter, I'll turn it over to you.
Great, thanks Tessa, and thanks everybody for being here. I'm going to introduce the project a little bit, and but then really turn it over to the panelists to do most of that. First of all, I just want to say this project on the last mile delivery systems is important from a number of respects, in my opinion. First of all, just from the technical perspective, it falls within the area of long-term autonomy within robotics, and in many ways, this is a grand challenge of robotics. The adjective robotic, people often take to mean as doing the same thing over and over again in a controlled way. But the challenge of robotics these days is to sort of get robots out of this sort of repetitive, doing the same thing all the time interactions towards robots that can exist in the real world with sort of dynamic features of people walking around, unpredictable effects, really being able to be robust to unforeseen circumstances. And that's really, being able to do that for a long period of time without people intervening is a grand challenge of robotics, and comes to play in many different sort of guises. It's of course in autonomous cars, as many people are talking about today, but also just robots interacting with people in the real world, and that's something that we're very focused on here at UT Austin. Another thing that this project is important for, of course, is it's within the context of our current pandemic, the COVID-19 situation, where we're all trying to go about our lives as much as possible, but in a way that minimizes and reduces interactions that could cause spread of a virus, spread of the pandemic. So being able to deliver things to each other without contact with one another is an important challenge, and that's what one of the things that motivates this project as well. And then finally, it's important within the context of good systems, the host of this event, where here at UT we have an interdisciplinary group of people thinking about what it means for a technological system to be good, and how would one evaluate whether a system is good, and then how would you actually go about designing a system that is good? And good in quotes. What does good even mean? And so this project sort of spans that those kinds of areas and questions, trying to, and the panelists who are going to describe it will talk about both the technical aspects and also what it means to try to think about putting robots into the same space as people in an urban context in a way that is good. So with that, I'm going to turn it over to the panelists. I'll first introduce them very briefly. Junfeng Zhao is an associate professor in the School of Architecture, a founding member, along with me, of the Good Systems Bridging Barriers project. Luis Senti is an associate professor in the Department of Aerospace Engineering and also a core member of Texas Robotics. Joydeep Biswas is in the same department as I am, an assistant professor within the Department of Computer Science, also in Texas Robotics. And Justin Hart is an assistant professor of practice, also in the Department of Computer Science, specializing in human-robot interaction, and the assistant director of Texas Robotics. So with that as introduction, let me turn it over to Junfeng to give a project overview and a short demonstration, and then we'll begin the panel discussion that will include questions from you.
Thank you, Peter, for the introduction. As Peter said, the last mile problem is a significant problem in our urban life. According to US DOT, 30% of our daily travel are less than 1 mile. This problem became even more important during the pandemic. We want to develop, people depend on the deliveries, and with the pandemic going on, we need a more hygienic system. So a group of scientists at the UT developed an autonomous delivery robot system that can provide a contactless and safe delivery service. Our team is integrating the work of several UT labs to make this idea a reality. So every delivery began with our iOS apps. You can imagine this is very similar to Uber and Lyft. It's a crowdsourcing shared delivery service. You can order delivery, and then we can basically record your address and make a delivery to you. Customer can follow their order every step on the way, just like we use the sharing economy apps. Our robot plan their delivery route autonomously and allow deviations for unexpected obstacles. A localization algorithm determines the robot's location in a mapped environment. The intricate system architecture streamlines communication between a customer and the robot. We have been working on several robot platforms. This include Unitree A1, Boston Dynamics Spot, and ClearPath Gecko. I have to mention at this stage, and today we will show the demo on ClearPath Gecko. So our future goal include our app will officially come to Apple Store in the fall, and we hope to run a lemonade stand as a proof of concept. We also want to work with the UT dining service to integrate our delivery service. Also, A1 and possibly Boston Dynamics Spot will be joining the delivery force in the fall. Last but not least, we want to thank our wonderful student from UT to make this event and project possible. This student come from very diverse background, from computer science, aerospace engineering, mechanical engineering, architecture, and applied math. I will turn the next step to Justin Hart. We will run a live demo to show you the actual delivery service. Thank you.
We seem to be suffering from a bit of demoitis. Oh, no, we're going. All right. So,
all right. So we would like to demonstrate a prototype of our last mile delivery system performing a building to building delivery on the UT campus based on a user request. As we run the demonstration, we would like to explain some of the technical challenges that we're working on addressing. But first, let me hand it over to Asha Jain, one of the students on the team, to start off the demo. Asha?
Hi everyone, I'm sitting here at the tower, ready to order a lemonade. You're watching my app, or my phone run our app. So I'm logging in using Google and UT authentication. And I'm now ordering a lemonade to the main tower. I expect it to arrive here at 2:25.
Right now, the robot is outside the Anna Hills gym, home to Texas Robotics, and it's off. So the robot that you see here is a ClearPath Jackal. It's running a long-term autonomous navigation stack that we've been building up over the years. The robot is equipped with several sensors, including a Velodyne long-range 3D LiDAR and a high-fidelity short-range depth camera for local obstacle sensing. All computation is performed on an onboard computer, and this robot can provide real-time live updates of its state to the system monitoring system on the server, and which relays its state to the customer app, which you see on the left over here. So a key challenge of such a project is the ability to be resilient to changes over time. As you might imagine, the route that the robot takes on one day might look visually quite distinct from the way it looks the next day. Right now, the robot's passing by a car parked on the left that you can see over there. Tomorrow, inevitably, the car will not be there, and there might be other obstacles there. Out in the distance, you can see some construction work, and the construction work is temporary. So how can you have this robot be resilient to these changes in the environment? We're relying here on an algorithm called episodic Nurmarkov localization, which actually uses a sparse map of only the long-term features. And these include things which are unlikely to change on the short-term basis, including the buildings in the environment. And everything else that the robot sees, the robot reasons about in real time. And what happens is that these long-term features help provide global corrections to where the robot is, while intelligently fusing this information with the pose-to-pose relative corrections that the robot reasons about with these short-term observations. I would like to also now to hand it over to Luis and Thies to talk more about our navigation algorithms.
Thanks, Joydeep. So at the navigation level, we have relied, as Joydeep mentioned, on LiDAR-based sensing and a modality of path planning called non-holonomic path planning, which is apt for this kind of wheel robotic systems. And then following prescribed paths and also incorporating feedback from the online localization process. In particular, feedback is one of the tools that allows us to respond to newly added objects and pedestrians that they were not incorporated during the mapping process. So allows you to be as safe as possible. Now, the next step that we are aiming is at incorporating some of these features for legged robots. Now, legged robots are very popular. They're starting to be very low cost and have some advantages of moving into a little bit more difficult terrains. And there is a few challenges. Some of them is the fact that technologies like odometry now need to rely, instead of wheel movement, they need to rely on legged kinematics. And that is both an exciting area and also a challenge. But also, these kind of robots, they offer new capabilities, such as holonomic movements, the fact that they can move in all directions. And this means that their ability to navigate into difficult environments is enhanced. And also perhaps the ability of moving closer to humans in crowds is also now possible. So now I'm going to pass the token to Justin, who will talk about architectures and other issues.
Hi, yeah. So I'm Justin Hart, and I specialize in both artificial intelligence and human-robot interaction. And when I look through that lens at this project, there are two big challenges that I really see. One of them is that, you know, as you can see, we're going through what would typically be a pedestrian space with lots of busy pedestrians. Right now it's a little empty, but we did see a few people. And the robot is going to be navigating directly alongside people. And, you know, using current navigation technology, that can be kind of disruptive. We want to be able to estimate what people are going to do. We want to be able to understand things like human gaze and body language in order to understand where a person is about to walk so that the robot can kind of get out of the person's way. And then from the robot's side, we want the robot to do something that's understandable to people. So we want to study what people do when they're walking through shared spaces in order to understand how the robot should be broadcasting its intention to those people. So when the robot's going down the sidewalk, it's not the case of a bunch of people, you know, feeling like this is a device that's in the way, something that they really don't want to be there, but something that is gracefully sharing the road and sharing the sidewalk with them. And then the other challenge that I've really looked at on this project is, you know, if you think about the current state of the art in robotics, we haven't standardized a lot on the sorts of development setups that one might have. If you're developing a desktop application or a cell phone application or a website, you kind of know what the stack is before you're starting the set of technologies that you're going to use. We do have a robot operating system, and Ross is good at getting all the components to talk to each other, but there isn't a real discipline structure yet in robotics, aside from the handful of architectures that have been developed, to say, okay, these are all the functions and we're going to be able to use them interchangeably. If you look at the challenge of fielding our system on a legged robot like Luis is talking about, and the challenge of fielding it on the Jackal like we're watching right now, there isn't a really great way to develop those top layers of software that are dictating all the logic of what the robot's doing and getting that to communicate down to the bottom layers. And that means that people who are doing things like application development need to think about things like localization and navigation to do that. When you think about the impact that that has on robotics, what that means is that people kind of have these one-off robots that do one thing. But what you want is something that's like your personal computer that can do a whole bunch of things. That's what will make robots economically viable to consumers. So with that, I'm going to turn it over to Junpei.
Thank you, Justin. As Justin mentioned, whether we like it or not, the robot going to be part of our life down the road. My research focuses on smart city and urban informatics. So in order to accommodate this change, we built an app for people, customers to interact with our platform. With this app, you can order short delivery service, and we can map out the estimated arriving time and the location of robots. Basically, just like you use a Uber app, basically we just replace a car with a robot. We built this app agnostic to any platform. Right now, you see a wheel-based demo. Down the road, we will build a leg-based robot, and we imagine this app will be launched in iOS devices and possibly in Android in the future. We believe this will be a good start to introduce the robot technology to day-to-day life and make people be able to interact with our future tools of in society. I will turn the talk to Aisha. Aisha will talk more about overall development of the app.
Hi everyone. As you're seeing now, the app is running, and there are many other features of the app that we can explore as well. Users can watch every step of the robot delivery from pickup to drop off, and watch the robot progress towards the current location. We can also see past orders and complain or write feedback, which is going to be really helpful to the team when we run our lemonade stand as a prototype in order to understand what sort of difficulties occur when delivering goods. Like Uber had to face when they first started up, it could be difficult to find your delivery robot or to retrieve the item from the robot. We imagine in the future, in order to secure deliveries to robots, there would need to be a passcode or on a box on the back of the robot. And this passcode would then be shared to the user via the app so they can unlock their goods. As Dr. Zhao mentioned, the app will be reaching the App Store sometime this fall, so we're looking forward to that, and that's one of our next steps. And we hope that more students on UT can try this app out. As I had shown earlier, the app login is restricted to UT students and to people affiliated with the university. That helps us do a couple of things. One thing that helps us accomplish is making sure that our users are trusted users. And the second thing it helps us to accomplish is to make sure that the robot is operating in a range where we have access to the robot and the area has been mapped before. So we look forward to implementing those steps in the future. And eventually as well, what we'll do is add a manager side of the app to be published on the App Store as well. This side of the app will help people run this sort of business, lemonade stand business. And the goal here is to see the status of all the robots and to provide a security feature should be any issue during the delivery. We expect that there might be issues with tampering or a robot getting lost or stuck, or there may be issues with like the robot getting stuck in the rainstorm or things that just are unexpected. So we hope that this part of the app can help trigger and detect those unwanted events, and then we can have some human involvement to prevent these security concerns.
At this point, there looks like there's a question on the Q&A about what is the maximum speed of the robot and how does it determine what speed to run in real time. So what happens is that we provide a nominal and a max speed to the system, which at the current moment is set to approximately 1 meters per second. Although the robot, we have demonstrated the autonomous stack navigating at higher speeds, including up to 1.5 meters per second. A key feature is that the robot reasons about the obstacles in its vicinity. It takes into account the current state and the acceleration and the dynamic constraints of the robot to modulate its speed to safely move around the obstacles that it's sensing at the same time and be smooth in its navigation. So while the robot is on its way to its destination, which is a UT tower, which is off to the left in front of the robot, I also want to specifically give a big shout out of thanks to the camera person behind the robot at the moment, Nick, and also Max, who's helping monitor technically the robot as we deploy it. A key feature that we want to make sure is that our robots are safe while we start out this rolling out these deployments. And Max is helping make sure that things are safe. I'm sorry, I spoke out of turn. I believe Chem is running the camera behind the scenes. So thank you to all of the students on the site at the moment running the demo. As you can see, the robot has reached the tower. And interestingly, while we started working on this robotics problem, you might have thought that the autonomous navigation would be the hardest thing to show. But what you're seeing right now is indeed that the robots reach the tower. But while we're relying on Wi-Fi, sometimes it takes a little bit of time for the Wi-Fi communication to catch up to tell the app that the robot has reached the actual destination. We hope to eventually move forward to an LTE-based system so that the robot does not rely on local infrastructure for this communication.
Hello everyone again. So I'm here at the tower. My delivery robot has just arrived and I can pick up my lemonade. As Dr. Biswas was mentioning, we are Wi-Fi issues and that's why the app has not updated. But I did get my lemonade and it's all safe and sound and now the robot is headed home. So here's our team. We really enjoyed working on this project, so thank you everyone who made this happen.
Thank you so much, Asha and Chem and Nick and Max and everybody who's there. Good job. And another customer well satisfied. There was a question in the Q&A about what onboard computer we are using. So the computer that we have on the robot is an industrial computer. It's just an Intel Core i7 quad-core processor.
Excellent, Asha and team. I'm so impressed. Congrats, everyone.
This is really great. I really, really enjoyed. It's great.
Yep, nice work, team.
So one thing that people, the audience, I hope appreciates is the, sort of the daring or the guts that it takes and the confidence it takes to run a live robot demo. So typically in a situation like that, the safe thing to do would have been to pre-record this and show a recording. This was hardware is always is sort of notoriously fickle. It's actually, I think, as was pointed out, that it's interesting to me as a roboticist and computer scientist that in this case it was the software app that had a glitch because of Wi-Fi, but the hardware delivery system, the robot itself, pulled off its mission without a hitch. And to be able to do that with we had no idea, the team had no idea before starting whether what people would cross its path, what car would cross its path, and yet had the confidence that to be able to run this live, and it was pulled off successfully the first time. So I think anybody who's worked with robots appreciates how impressive that is. If you haven't worked with robots, take my word for it that this is a really great feat and bodes well for this project as a whole. So I think Tessa, I think you wanted to turn over a poll at this point to the audience. Is that right?
Yes, that's correct, Peter. Thank you. And thank you for that demonstration. So we would just like for all of our attendees to respond to this poll so we can get a sense of how you think robots will be integrated into daily life over the next 10 years. And as you're answering this poll, Peter, I'll go ahead and turn it back over to you to start our panel discussion.
Great, thanks, Tessa. And I think we'll have a couple of polls after this as well. I'll point out that the third option here you should sort of consider as already the case. We'll certainly see that within 10 years. We do have robots in warehouses, and they're starting to be autonomous vehicles on the roads. So this question is, do you think that's going to be as far as things progress, or are you more optimistic to choose one of the upper options? So I encourage everybody to give your answers, and we'll feed that into our discussion. I guess my first, so I'm going to now ask a few questions to the panelists, and again encourage everybody to use the Q&A feature if you'd like to me to mix in questions of your own. But let me start with you, Junfeng. So coming from the School of Architecture, this is a robotics project, but it's really also about how do we imagine built spaces. And so from your perspective, how will urban infrastructure and policies need to be adapted or be adapted for short to medium range delivery system? Do you think that it'll just be using existing infrastructure, or will we need to build designated mobile robot lanes? This demo was all on existing infrastructure, but of course the robot was going down the middle of a street, and we saw a car have to move around it. So what do you think this means from the perspective of the built environment?
Thank you, Peter. That's a great question. Just before I answer this question, I want to just remind audience, when you see the scooter first come to Austin, what do you feel? So just imagine down the road, if you have a 10 times more robot rolling on the street, how do you feel? So from an urban planning, urban infrastructure perspective, we technically introduce a new transportation mode to existing structures. So in some cases, we definitely need to build a designated robot line for them to move around. In some cases, maybe if the delivery volume is low, we can use existing infrastructure like sidewalk and bicycle lane. But in my opinion, down the road, we're going to be ready. We're going to significantly increase our infrastructure capacity specifically build many designated robot land. That's for infrastructure perspective. For policy perspective, again, we technically introduce a new transportation mode to the existing urban system. We have to change our policy as well, how robot can interact with the existing car, bus, or bicycle, or pedestrian, or how we interact with the robot who are going to be reliable for the accident. That's something we are to think about as well from policy perspective.
Great, thank you. So there's been a few questions, and I want to sort of wrap them into one and turn it over to the entire panel that are sort of about robustness. So in the demo that was shown here, it's a Friday afternoon in the middle of a semester on the UT Austin campus. That would typically be a time where there's really lots of people walking around. Of course, because of the pandemic, there weren't that many people. But can you tell us, how robust the system would have been, and how that demo would have looked if if it had been between classes in a normal year and there had been lots of people around? Or what about if there was rain or dust, or if there were construction that's not on the map blocking the marked path? Would a human need to intervene in that case? So just all of these sort of robustness questions wrapped into one. And let me just add, any of the panelists who wants to respond to that, please do.
I think there are several parts to the question, and maybe we can answer the different parts as most relevant to us. I can tackle the part about the perception challenges that were raised here. As you might imagine, on a day with inclement weather, where either you have puddles on the ground with reflections, that can be confusing to our perception algorithms, and because of limitations of our sensors. As of today, indeed, the robot might require human assistance in overcoming these things, but this is part of our research agenda. Some recent work that we have done has been on what we call introspective perception, which allows autonomously deployed robots to actually detect failures in the real world, understand and reason about what are the root causes of them. So for example, is it a reflection from a surface, or is it a shadow? And then actually try to work out a mitigating scenario where we try to learn context-aware, specific, robust loss functions to overcome these limitations. So that just gives you a flavor of some of the directions where we're headed. Indeed, the answer is that perception in these varying environments is challenging, but we have a research agenda to address some of these.
Good. Thanks, Joydeep. So before the next question, I'll just comment that the poll results for the first poll did come in. And actually, interestingly, it was almost split evenly, 1/3, 1/3, 1/3. So about 16. Well, I guess roughly 36% of the people think that we'll just see autonomous vehicles on roads and in warehouses, and then 48% say that the people will start seeing robots in public spaces. So I guess that was the most popular, but not by a huge margin. And then 39% said that we'll see robots actually in our homes doing chores other than vacuuming. So thanks everybody for those responses. Before going on to the next audience question, let me ask a quick question specifically for you, Justin. So if you were to compare the development of robots with the development of personal computers over the past 70 years or so, where would you say that we're on that journey?
Yeah, thanks, Peter. I think that this is something that I think about a lot, because one of my goals is to see a robot in everyone's home, right? The big transformation when that happened to people was in the 1980s, when people started purchasing personal computers, when the personal computer was developed. But you're right that, of course, the development of computers lasted 70 years, maybe even 80 years ago, if you think about it, going all the way back to World War II and before World War II. We're at a point now where we have robots in very specialized environments that are tuned to robots. And if you look at, maybe the 1960s and 1970s, we did have computers that would do sort of one thing that were too big and too expensive for a home user to use. And there were a lot of steps in the process that we went through in order to get from point A to point B on giant computers that took up a whole building and had a few kilobytes of RAM and could do basic addition and subtraction, to cell phones and the types of computers that ride around our robots. I think that a lot of that had to do with just taking a very disciplined look at what needed to happen to standardize things. I think that a lot of what we do now in robotics is stuff that is developed towards these one-off applications, because the person who's developing the application probably also has to understand manipulation, probably also has to understand navigation. If we get to a point where we start to compartmentalize those things, like the standard libraries that you use to develop desktop applications for a personal computer, then we can get to the point where we can start to have more general purpose robots that do more than one thing. And I think that, we have seen a big explosion in robotics research, and there were a lot of pieces that played a role in that, including things like ROS, but more standardization and more just understanding what the pieces are that everyone wants when they're developing those applications. I think that that'll go a long way. If I was to put it on a timeline, I'd say we're kind of in the 1970s right now with robotics by relation to computers.
Good, thanks, Justin. And actually, on that topic, there's a well-known quote from 1943. It may be apocryphal. I couldn't find a source for it, but it's plausible, which is that that somebody in 1943 would have said, "I think there's a world market for maybe 5 computers," and in 1946. Somebody by the name of Sir Charles Darwin, not the Darwin of evolution, but another, says it's very, very possible that one machine would suffice to solve all the problems that are demanded of it from the whole country, right? So there was a time in the early development of computers and PCs where people weren't envisioning them being nearly as ubiquitous as they are now, where we have a computer in our pockets. In fact, Ken Olsen from which company he was from, but again, one of the mainframe companies said there's no reason anyone would want a computer in their home, and that was in 1977, right? So there's been a huge transition in the PC and robotics market, and we're not there yet with robots, but yeah, it could happen. So before moving to my next question, let me ask another question that's been asked by the audience and also upvoted several times. So, and this is for anyone on the panel. Can the robot reason right now about its remaining battery life? So, say it has to make a delivery across campus, but the battery will die before it reaches its destination. Is the order then handed off to another robot, or does the scheduling system reason about that before handing it off to a robot? So is this right now set up as a multi-robot system, or is there just one robot? How does it monitor batteries, and what are the plans for the future in this regard? Any panelist?
I can start. We definitely develop this system for multi-agent, multi-robot system. Right now, we only have one robot running. Ideally, we will have a different depot, like a robot nest for delivery service, and we will calculate the shortest distance and also monitor the battery life during delivery service. In a short answer, we build this system to include a robot to run on the system.
Okay,
let me. I just want to comment there that if we are using that, that there is a need and an intention of doing it, and if we are delivering items, supplies, then there is an extended area of this delivery system, which includes robotic arms as well. It makes the problem more complex, but then that allows you to do handovers from robot to robots, and that's definitely on our radar as well.
Great, thanks. Thanks, Luis. And I'm going to come back with a question for you in 1 minute, but before I do, there's another poll, which is what daily tasks would you like robots to perform for you? So there's a couple of choices. There's 4 choices there. So I encourage participants to answer that poll, and we'll see the answers. And that's actually very relevant to the question I'm going to ask to you now, Luis. As you're a founder of a robotics company called Apptronic, and so from the perspective of that kind of experience, what do you see as some of the future applications for this SMAD system that's been demonstrated here today? And what would it take to bootstrap a startup company if you were going to try to build something around this kind of a system?
That's right. I think that at the urban level, there is an opportunity for turning some of the commuters that we currently have, the scooters and the new bigger wheel bikes, into adding more autonomy and providing a service where these systems, they go to the charging station, or they coordinate movement towards a place to gather from the weather. So that sort of takes a little bit of the lessons learned from this technology we are developing, and then putting it into an already existing system to augment it. I think also that avatar technologies, the ability of remotely connecting to multiple systems, where it's on the street or at home, is right now a very hot topic, and we want to again have this ability that we saw today into systems that operate maybe into more cluttered environments, not only among crowds there was talk about, but then inside our homes. And again, there's a lot of lessons to be learned to what we've seen, and perhaps turn this technology. Right now, this technology we've shown is for deployment within campus, is a sort of is an academic effort. But then if this turns to be, ultimately, we want to push our students and our faculty to create startups, and that might happen. And that's maybe some of the areas that we should move forward. And thankfully here at UT, we have these wonderful services for entrepreneurial pursuits. The Center for Innovation provides grants, a bootstrap, allowing students and faculty to bootstrap companies. Actually, this is how my company started a few years ago. And here in the US, obviously, is paradise for launching these kind of efforts. Some of the programs, if you don't want to use personal funds, or it's too early for you to look for venture capital investment, then is to leverage some of the federal programs. And we have these, again, wonderful programs: SBIR, small business grants, and STTRs, technology transfer grants from public institutions to for-profit institutions. And a lot of this money also comes, not only from programs like the National Science Foundation, but the Department of Defense is a great resource for bootstrapping technologies into the commercial field, especially those that have dual applications, those that can support logistic operations in the Department of Defense, but also can now help for transportation and home care and other capabilities in civilian environments. Obviously, the route of family offices, venture capital funding, international investors continues being a very important resource. So thanks, Peter, for the question.
Yeah, great. Thanks, Luis. So I'm going to turn now to another audience question. And this may be for to start with for Junfeng, but any panelist as well. And that's, what are the challenges and opportunities for the public developing trust and acceptance for robotics to become more integrated into a community fabric? And maybe touch on the sort of the elephant in the room with all forms of autonomy, which is what are some of the issues surrounding job impacts on jobs and sort of the careers of people who are currently doing the jobs that robots may be doing. So John, it's a general question, but just from the trust perspective, maybe you start off.
Yeah, thank you, Peter. I just feel like that's a great question. So for robots, again, I'm a firm believer robot can enter our life just like a personal computer enter our life. So one thing is to build a trust for robot. To build a trust, we have to allow robot to help us to do some certain tasks, just like the poll showed. We want to robot to drive us or mow the lawn and so on and so on. We want to introduce this step by step, not all at one time. We want to introduce robot to our daily life. We want to coexist with robots. That's how we build the trust and perception safety between robots and human being. Also, when we design the robot system, I would say we want to consider ethical design as well. So we want to design and build a robot who can serve our society in a good way. So that's my short answer.
Good. Anybody else want to chime in on that?
I think maybe another way of thinking about it also is that we really want our robots to be force multipliers. It shouldn't we envision a future where they're not displacing humans, but allowing the same humans to do a lot more. It's one thought.
Yeah, that resonates with me as well. I would say, you know, when I'm asked this question, sometimes I think it's useful for people to think of robots not as replacing humans, but as just a different species, right? Of another being that has different capabilities, different limitations, that can, you know, that it's up to us to try to find what's the way to have them complement humans, as Joydeep was saying. Just comment on the poll results that in the second poll that there's, you know, the largest majority of people said they'd like to see robots drive to work and mow the lawn, and then relatively fewer on making the bed and feeding the kids. But you know, of course, there's a lot more around the home chores as well that we can envision. Let me actually, so Joydeep, since you just answered, let me turn over another question to you, which is, can you tell us what really is the long-term autonomy all about, and what are some of the biggest challenges with long-term autonomy?
So one of the challenges, one of the biggest challenges with long-term autonomy is that we have technologies today which under nominal conditions work great for 5 minutes or 10 minutes when we deploy them. But the challenges with long-term autonomy is that when you try to do the same task with the priors that you built the previous time, inevitably things have changed. And coping with this change is actually remarkably hard, it turns out, for state-of-the-art algorithms. Adding things to the environment is something which is easy for us to reason about. Removal, where we saw something yesterday, but it's no longer there today, and now we're expecting it to see it there, and if you don't see it there, the robot gets confused. That is actually part of the challenge of long-term autonomy. Another challenge that shows up in long-term autonomy is that over short periods of time, you can trust that unusual circumstances will not happen. But from experience, I can guarantee to you that even the most unusual circumstances are become likely to happen over extended periods of time. So things which you might think might never happen eventually do end up happening. And the third thing is that when you start deploying these in unstructured environments, they're exposed to scenarios which the roboticists never even dreamt about or thought about. And it's really up on the robot and these algorithms to deal with these scenarios on the fly and do things correctly. So I think those are the main things which come to mind about this long-term autonomy.
Great, thank you. Let me ask just actually, you know, I'm going to jump from one end of extreme to a fairly technical question that may have a brief answer, and then to a more broader ethical-based question. So the technical question for anybody on the panel is what navigation algorithms are in use on this robot? Is it using D star, A star, RRT star, and how do the algorithms that are being used relate to those existing systems?
Yeah, so we have a hierarchical planner on the robot. At the high level, planning which routes to take on campus is done using A star on a graph, and this graph specifies the nominal traversable pathways on campus. And what happens is that at runtime, every time step, the robot checks whether this plan is valid, and if the plan is valid, it projects that plan into the local frame of reference of the robot, and then it finds an intermediate waypoint on the plan. Now this intermediate waypoint is then used for a local planner to plan for taking into account the obstacles as well as the dynamic constraints of the robot. And this local planner actually operates in a space which reasons about the exact pose of the robot, its dynamics, as well as everything, all of the entities in the scene around it.
Yeah, I wanted to add to that moving towards as well the legged capabilities, search plays a very important role as well, but of another caliber, because in that case, you might be concerned about the particular kind of local features of the terrain, whether there's a rock, whether there's a staircase, and or a complex, clutter feature. And there, the search has to be over what is called the footholds, where you're going to be placing the footholds. And that depends very much in something called the robot kinematics, which is the degrees of freedom that it has. And fortunately, that kind of search, which is a little bit higher dimensional than other type of robotic systems, now is speeding up. There is a lot of math tools, spatial algebras, for instance. And then, of course, machine learning tools for speeding up the computation, for performing this complex maneuver, a little bit more different than moving from large terrains, more kind of in the local environment, if you will.
I think that there's one more piece of that, which is that, as I mentioned earlier, we're looking at navigation in the presence of people. And we're developing specialized algorithms to do path planning around people, both to react to the people appropriately and to broadcast the right type of either signaling or body language or whatever it is that allow people to passively understand what the robot's up to.
Good, thanks everybody. So, so as I said, that's sort of on the technical algorithmic side of things. Now to sort of go to the other end of the spectrum, there's a lot of sort of thinking in news and press these days around the incorporation of inherent biases into machine learning algorithms in general. And sort of famous examples of training sets only on a certain demographic of people, then coming up with results that don't generalize to other demographics. So what, if any, issues of this sort are come up in the kinds of sort of last mile delivery systems that you guys are creating and considering, and how can they be countered? How can we overcome any inherent biases from the robots creators when developing a system like this?
Well, I can start on one sort of obvious thing, which is that we're developing and deploying this system on the UT campus, which is structured a certain way. It has only college students on it, has only UT college students on it. What you need to do, at least in terms of data sets and at least in terms of reacting to your environment, is to try it in different environments, move it around. You need to have a deployment somewhere else so you can transfer it into the environments, hopefully targeting not some specific environment, but doing a broad spectrum of different environments that it deploys in. And this, of course, overlaps with everyone's interests. This is sort of a long-term autonomy type thing. This is also just how do you craft your data set and how do you craft your test.
I want to add to Justin's answer. So I think that's a great question. So in order to avoid bias or reduce bias, we employ, at UT, we have a good system, which is a multidisciplinary program and a grand challenge. So scientists come from different backgrounds working together on one project. So we complement each other and provide different perspective. To a certain degree, this will help us get a big picture of the problem and avoid bias to a certain degree.
Yeah, I want to add also that bias can happen in things that are very geometric, like there is certain statistical models for or the variance of the movement of people, and then the distances to keep for safety. And of course, the way that people are navigating depends on things like cultures, for instance. Even whether you walk on the right side, on the left side, and the body signaling. Justin was talking about the social cues as well. And definitely, I think that training these systems with diverse populations and continuously training across all sort of groups is the best antidote for these problems.
Good. You should have all seen our third and final poll. I hope people responded to that. Yes, they did. In fact, the audience answers which tasks do you think are difficult for robots? 18% said planning and navigation route, 76% said avoiding oncoming traffic, and 42% said detecting humans. Joydeep, do you want to comment on how that lines up with reality?
I think that's a really good depiction of the reality, actually. Given a graph, like planning a navigation route is something which we've known how to do for a while. There are lots of classical algorithms to do that. Detecting humans, like in the sense that if you have an image, finding a bounding box of a human is something which used to be a big challenge. And then in the age of the rise of deep learning, this turned out to, there were many good solutions. Avoiding oncoming traffic is a very interesting open-ended problem, which in some cases I feel it might in fact be AI complete. Imagine a scenario where you see some oncoming traffic, you have cones on the road, and a person in a traffic vest is directing oncoming vehicles. So to be able to cope with this scenario, the agent needs to be aware of what are the relevant things, that there's oncoming traffic, that there's information provided by this other human. It just requires reasoning about so many different things, and not just about geometry, not just about a single entity recognition, that it almost feels AI complete. Indeed, I don't think, not only are our robots not able to handle all of these general problems today, I feel like this is almost getting into the problem of we're not even sure how we might start to think about some of these things. It's just a quick thought.
Yeah. Good, thanks for commenting on that. There were a couple of technical questions that we can answer quickly before we're running low on time, so I'll have just one more question after that. But from the chat, somebody asked, are you guys using ROS or ROS2? And that the panelists have answered that right now it's ROS. There hasn't been an upgrade to ROS2 yet on this system. And then also the question, is mapping done with ROS Cartographer or some other solution? Joydeep, do you want to comment briefly on that?
Yeah, so we're relying on several of our previous projects, including Nautilus and Human in the Loop SLAM and long-term vector mapping. And what these algorithms allow us to do is actually to build not what's an occupancy grid map, which is what you get out of many of these algorithms, but vector maps and vector maps of long-term features. So if you go to our lab website, you'll find links to several of these open source packages.
Great. So maybe I think we have time for one last question, and this is from a broader perspective. It's a sort of an infrastructure and policy question. So what are the panelists' thoughts on balancing over-regulation of robot technologies, but at the same time having enough oversight to ensure efficient and safe deployment? So this sort of, Joydeep, you said that it's an important consideration that the robots always be safe. What's the balance here between ensuring safety and allowing for innovation? Any panelist?
I've been thinking about this. I could go with that, but I think Justin and Luis and Junfeng have also thought a lot about this. I feel like one of the things that we want to be sure that we want to allow room for is that robots today aren't as capable as they will be in the future. And as with kids make mistakes, but we want to allow them to make mistakes in a safe manner. I feel like some of the philosophy does transfer over even to robots. How can we allow robots to make mistakes, but not catastrophic mistakes? And there's some balance there. I'll hand it over to Justin.
Yeah, any other panelists?
Sure. I think that I've got pretty strong opinions on this, but I'll try to give measured responses. I think that in the past we've erred slightly too far in the direction of safety, because you can limit the applications to which the robot can be deployed. If the robot, for instance, has to move too slow to be useful as a delivery system, then that's an error, right? You need to be able to move fast enough that people want to use the device. Or if you look at older robots in factories running G-code that absolutely must be isolated to a work cell, and they're very strong and they could really hurt you if you walk in there. And yet you want to be able to have newer, smaller, lighter weight robots that are able to interact directly with people in order to get practical work done. And when you're applying rules that were designed for a giant thing that can lift a car to a small thing that could handle something like a paintbrush or insert a screw, that's just the wrong approach. I think that if you look at the way that we deal with safety in other consumer products, that might be a way that kind of leads down the path of having practical deployed robots. Like if we have a car, we crash test the car, and maybe we're not at the point where we should be crash testing robots just because of expense. But you could probably do some more testing of that nature to get us closer to a set of reasonable regulations. And of course, that's going to be collaboration between policymakers and engineers.
Good, yeah, and I'd like to just follow up on from my own my own perspective. We all have to be mindful, people developing technologies, that accidents, if they do happen, can really set back public acceptance and trust, which we talked about earlier. Even if autonomous cars reduce the the number of fatalities on the road by a huge amount, a single fatal accident causes a lot of press and and sort of notoriety and fear and lack, sets back the ability of the rate of public acceptance. And so we do have to realize that people are watching, and until people are comfortable with the technology, there can be big consequences to catastrophic errors. In any case, to be mindful of time, we are at the end of the hour. I think it's clear to everybody. I hope it's clear to everybody who's joined in here that this is the beginning of a very exciting project. You were able to see a very successful demo. There's a lot still to be done, a lot of open issues as touched on here. But really, as I said at the beginning, an important project from the perspective of long-term autonomy, from the perspective of good systems, and from the perspective of using robots in the time of a COVID, of a pandemic of any kind. So thanks everybody for all of your questions and for joining us today. If you'd like more information about this project, you're invited to get in touch with the panelists or myself directly via email. We'd also like to invite you to join our mailing list, and there's a link to do that in the chat. Keep an eye out for an email also with a recording and a follow-up survey. So I do want to thank again the UT partners who've been working on this project with Good Systems, the Autonomous Mobile Robotics Laboratory, Human-Centered Robotics Lab, Learning Agents Research Group, Texas Robotics, and Urban Information Lab. And especially the people behind the scenes, Tessa Green, Andrea Christel, and others who've really put this program together, brought the panelists together, and made sure that the technology ran smoothly. So thanks everybody for attending, and we hope to see you at another Good Systems program soon. Goodbye, everybody.
Thank you. Goodbye.
Thank you.
Thanks everyone. Bye now.